Okay, so we can start. So we were doing diffusion models, and so this is the content. We will start with hierarchical VAE, then we will make it a little bit spatial with Markovian VAE, and then we will go into variational lower bounds of this Markovian VAE, and then we will see the explicit terms there. So hierarchical VAE, we did this. Okay, so basically it's a hierarchical form. We can see that as a hierarchical form of VAE, and this is VAE. We have done this before, and this is the basically the graphical model of VAE. So there is an encoder and there is a decoder. So we have written this in a slightly different way now, in a cyclic way, as you can see. Earlier we used to write like this, right? So this is encoder and this is decoder. So the idea here is that we want to kind of stack more of these, okay? So we did that, and if we do want to stack VAs side by side, then how are we going to do that, right? So will it be a kind of a chain of nodes x1 to, in this case, let's say x1 to x5? And if it is going to be a chain, then how are they going to depend on each other, right? So if I have x2, it depends on x1. If I have x3, it depends on x2, but it also depends on x1. Okay, and if I have x4, then it depends on all previous ones. So that's one naive way to model this dependencies. So that was forward case, right? And then we can also see how we can model the dependencies during the decoder phase, right? So this is decoder and this is encoder. Unlike VAE, we want to go it multiple steps, and this is your encoded let's say data, random variable. Usually we will treat that as some Gaussian, and then you want to reconstruct the original image, but obviously the way our model is, you won't go one sort. So you want to model it like a chain. You will go one step at a time. So again, here there are modeling assumptions. Should you consider dependencies like this, which are quite dense in some sense, right? So, and if we do consider that, then the joint probability can be given by this, right? According to this graphical model, if we look into the forward process, let's say, then only this direction, let's say, then the joint PDF will be given by this, right? And we write this like this. So we start from 1 and then the parent of xi and so on, right? So these are the modeling assumptions, right? So if we do this for this specific example, then the joint distribution for the forward distribution would be given by this, and similarly if we do the backward, which is by P, and this is the forward by Q, then this, according to the dependencies, this will be the one, because Z5 doesn't depend on anyone because it's the root. So Z5 is kind of indifferent, but Z4 depends on Z5. Z4 depends on Z5. So these are the modeling assumptions. So Z3 now, according to this, depends on both Z4 and Z5 and so on. Okay. So we thought about that, right? So should we consider all possible dependencies, or should we simplify? If we do simplify, then as you can see in the forward process, we have kind of got rid of those additional arrows that we used to have, like this, right? And like this, right? So these arrows are kind of gone. So this is the simplification we did, and this is what Markovian means, that the current state only depends on the previous state. That's it. Okay. So with Markovian assumption, things are quite simplified now. So this is the forward process, and this is the backward process. So basically your encoder will take an image x1. It will produce a series of latents, not just one latent as in VAE. Now you will produce a series of latents starting from Z2, Z3, Z4, and you end at, let's say, Z5. And then you will try to reconstruct the image by going backwards. Okay. So Markovian assumption simplifies a bit. Now again, should you go, because this is the sampling process, right? So, and this is in some sense a current research topic also, that okay, in the forward process, let's say you add some noise gradually and you arrive at some pure Gaussian noise. But then backward process is the sampling process where you really generate. So you sample something from standard normal and you want to generate the data. So this is a kind of a bottleneck in terms of research. So many of the recent papers are focused in kind of making this sampling faster. Okay, because the natural research question is like, do you really have to go step by step to generate? Okay, so in that way it's like several orders of magnitude slower than GAN. Okay, so this is research topic. Several ideas are being considered, like consistency model. In 2023 it came, okay, and then there are Schrodinger bridges, so you can make a lot of bridges kind of stuff. So but we will come to that. Okay, so we will come to this process, but for the moment we keep it simple, Markovian, and it goes follows certain time steps. Okay, if we combine both forward and backward, so this is our encoding process and this is our decoding process, which also happens to be the generation process. Now we have to obviously fill the details. So we can use some notations for the distributions that we generate at each time step. So a forward transition from xt minus 1 to xt is denoted by q xt t minus 1. Okay, so basically this is a distribution that generates xt given previous time step sample xt minus 1. Okay, so you can think of an image that is being propagated, and then the question is, given this image, what would be the propagation of that image? So it will be via some probability distribution, right? So you would like to learn the probability distribution that will kind of help you sample from here. Okay, so these are the probability distributions for the forward process. Okay, and similarly we would like to have some probability distribution for the backward process, and so we have p theta and we have q phi. So these are the q phi and we have p theta. Okay, now theta and phi suggest that these are parametric distributions, and as you know by now, by parameters we always refer to some kind of a neural network. But you will see some simplification. Forward process we will not use any parametric neural network in the forward process. Okay, so you will see that. However, the backward process, which is also called the denoising process, we do have to use some parametric distribution. There we cannot kind of get away with that. Okay, so in this generic way, in this generic model, we have this is Markovian, this is and we have both forward and backward process now, and we can write down the joint distribution assuming which one you want. So let's say for the p, then it's this way we are looking at. So you forget the arrows that are going this way, you only look at the arrows that are going this way, because that's like represented by p. So this joint distribution the random variables involved are x, which we generically write x, but it's like x naught, let's say, and then the intermediate ones are like z1, z2, and something. Okay, so there is a dot 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 here, meaning z1 up to zt here. Okay, so we can consider a joint distribution of all these random variables. Okay, and again via chain rule this comes out to be like that. And this is for this process, right? So backward process denoted by p. So basically it starts from zt, which is the root. So as you can see from the chain rule formula, for the root we have just p zt, because it doesn't depend on anything else. And then you can pull out this additional term just for this part where you went from z1 to x naught. Okay, just to treat it separately. So you may pull out this guy, x0 given z1 from the product, and then remaining ones are kind of recursive. In the intermediate ones are of the form zt minus 1 given zt. Okay, so And then if we look into the Q distribution, so Q distribution is when we are producing latents given we have the samples X. So in this way, we will look into the graphical model that goes in the forward direction only. So you forget about the backward arrows, or look at the forward arrows. So in this forward arrows, obviously, you can again pull out the first term, which is this guy. So the first latent that you produce Z1 given X node. So just keep this out because these boundary nodes will be treated kind of in a special way. But the other ones are the you can just keep it. Yeah, in this case, you don't pull out the boundary one, which is the capital T one. So you can keep it up to 2T. Okay. So these are the next latent that you produce at time T, given the previous latent that you had at T minus 1. Okay. So this is the joint for the posterior distribution. Okay. So now let us do the elbow bound for a Markovian VAE, and we have done this for VAE previously. So let us look at the math. So what we usually do is that we write down the graphical models of whatever modeling we have, and once we have and these are mostly latent variable models. So we have samples, and then we have certain arrangements of the latents. Okay. And obviously, our goal is to get the likelihood estimate, right? So log likelihood. So we want to estimate this eventually, right? So given set of samples, what is the probability distribution we have? Basically, it means that you have to do the log likelihood estimates. So you have to maximize the log of the probability. So this means that P, which was the joint. So P is this guy, right? So P is written as this joint, right? So in this joint, in this graphical model, you have multiple random variables. You have obviously the interesting one input, which is the samples, okay, cat images or whatever, okay. But the ones that you have, the other than X, which are the Z hairs, right? So these we call latents, okay. Now these Z, obviously we don't want them, okay. Of course, it's a joint distribution and all the random variables are involved, but what is really important for us is the X one, okay. So hence we will marginalize this joint distribution with respect to Z. So in this joint distribution that contains X and all the latents Z starting from 1 to T. Okay, sometimes there may be a misplaced notation, I don't know, from the figure, and this maybe Z starts from 2 or Z starts from 1 and initial X was X0. Okay, so I hope that does not confuse you. So let us say we had X and then all the latents starts from 1 to T, and this was our joint, and obviously we have to marginalize out the Z. So if in a joint distribution we marginalize out then all the Z, integrate out all the Z, then obviously we will be left with P. Okay, so that's the idea. That is what we have done in VAE, and this is in this case just that there are many Z now. Okay, in VAE there were just it was just PXZ DZ. So we just had one latent, but now we have to integrate out with T of these latents. Okay, so that's like the first step. Now second step, as in VAE, we introduce this Q distribution here, and we multiply and divide by the Q. Okay, and this, why we do that? This helps us in getting into some tractable lower bound. Okay, as such this is not tractable, but with this introduction of this Q, things become tractable as we have seen already in VAE actually. So it's an extension of that. So so we have Q phi introduced here, right? So now we will see what lower bounds we can get from here. So this is fine. Multiply and divide by Q phi. So it remains an equality here, and then this could be now written as an expectation of Q. Okay, so you treat this function here, and this is the PDF. So you can think of this guy okay, being taken expectation with respect to this PDF, right? This is how we read the expectations, right? So this is what is going on here, and this is again a similar trick as in VAE. So we wrote this as an expectation of Q phi here, okay, and then we use Jensen's inequality. So it applies on convex functions. So f of the average and we is because log is concave, so it's other way around now. So log is concave. So in that case, f of the average is less than equal to now. Okay, average. Okay, less f of the average would be greater actually. Okay, so that is greater than equal to average of f, right? So our f is log here. So log of something average, okay, is greater than equal to average of the log quantity. Okay, so this is Jensen's inequality. We have also seen this in VAE case. So now we can insert the joint distributions that we wrote. So above we have the joint distribution for the backward process. Again, backward and forward may be defined a bit differently in different blog or something like that. But in our convention, P is like backward, okay, and Q is forward. So so P is like the generator, okay, and okay, so we can write down, which we already described what these joint distributions look like. So we just substitute those here, okay. So this is for the top one, this was the joint distribution, and for the bottom one, this was the joint distribution. So yeah, so we are here now. So so we leave this term here for the moment. Yeah, we could have gone further here and derived some more expressions here, but we will do a slight modification from here onwards, and that's where we will have this variational diffusion model. So we will do some slight changes before we proceed. So if you look at this figure right now, you can already notice some changes that we did, okay, before we want to go forward. There's a hierarchical VAE. So the changes that we have, you can already see. The first one is we prefer to replace Zi by Xi. Now, replacing Zi by Xi is not just a notation thing. It also means that the sizes we want to keep the same. Okay. So earlier, when you see VAEs usually will always kind of take the X to some lower dimensional space Z. Okay. So this was always like this. Okay. And that's why we use this Z, which are kind of smaller. Okay. In size, because they are getting compressed somehow. Okay, and so one of the changes we want to do is that no, we don't want to do compression as such. We keep the same sizes X. Okay, so the significance of Z being replaced by Xi also means that these X1, X2, X3 are of the same size. Okay, so this is what I have written here. Also, what we have done is we remove the parameterization of the forward process, which is the Q phi. Okay, so in our original model in hierarchical VAE, we thought of using some parameterized network here, right? Q phi and so on. Okay, so there is a mistake here. You can see these are all Q, and these are all P. That's correct. Okay, but we dropped the parameterization for the forward process. In VAE, it was used. Okay, the encoder was a parameterized neural network, but here we don't want to do that. Okay, so you can already see the plan that we have. Our forward process Q phi is not long. Basically, phi is dropped. Okay, so we will see that we will. What we will do is that we will we will consider them as Gaussians, and these Gaussians mean and variance will be changed explicitly. Okay, and it will be done in a way that this gets into pure Gaussian. So it's possible to do that. We will see that. Okay, you don't necessarily have to use parameterized neural network to get to pure Gaussian. Okay, so that's the one change we will do. That's where we are kind of diverging from VAE now. Okay, so forward process is like independent of learning because there are no parameter. No learning happens in the forward process now. Um, so it will be Q is assumed to be linear Gaussian, okay, and that is easy to propagate. So we will derive those expressions explicitly. So basically, given an xt, how will I produce xt plus 1, right? So this is something we want to see, right? So what is the distribution, okay, that will, from which I will sample and I will get xt plus 1. So this is something we want to impose that it is Gaussian, but we want to see the explicit expression, right? Gaussian in general, but how will I generate, right? In practice, in algorithm, right? So that is something we will try to fix. Okay, what exactly will be there? Okay, so and finally the PT that we will get, PT corresponds to this, the final distribution that we have. We aim for getting into standard normal. Okay, so standard normal is good because, as we know, we will sample from there, and then our plan is to kind of follow this backward process and create samples. So these are the changes we did, okay, in variational diffusion models. Okay, so yeah, just some more remarks. So in VAE, encoder was assumed to be trained and trained KL to, and we trained it via KL to standard Gaussian. It was via neural network, and so on. So and it was in one sort in VAE. Obviously here it won't be one sort. I mean, just this is our plan. So these are just remarks. So in variation diffusion models, we want to do similar but not one sort. We want to arrive at the final standard normal distribution at t equals to t. Is there a way to arrive at pure Gaussian noise? So these are the questions now. Okay, so the plan is laid out and how we are going to do that. Okay, so so this is the plan, and this plan we will go through quite a few derivations to arrive at that. So you can think of this for the moment as as a plan that we define the encoder's mean. So first of all, we see this as a Gaussian distribution, right? So when we say that this Q is Gaussian, then we have to tell what is mean and variance. Then it will define a Gaussian, right? So we say that it's Gaussian, and we will define mean to be something like this. So obviously their details are missing. You know xt because you will start from x0, so you will know x1. Let's say you will know x2 and so on. So basically you will know xt minus 1. But what is square root of alpha t is something we will try to see. Okay, for the moment keep it abstract, and that the mean of the new sample xt in the forward process will be some square root alpha t times the sample itself at t minus 1, which is xt minus 1, and we will define the variance to be like this. Okay, so from here if you see, so if we write down q xt given xt minus 1, so this will be normal according to our plan, and normal with mu xt and sigma t xt. Okay, so the plan is kind of laid out like this. Obviously we have to specify what is mu. Basically we have to specify only alpha. Okay, because alpha defines both mean and variance. And xt minus 1 keeps getting propagated. So once you have x0, you know alpha, then you know the mean and variance of x1, and then you know alpha 2 again, so you know mean and variance of x2, a normal distribution that will produce x2, and so on. So basically everything now boils down to alpha that we will see. So this is the plan, that our encoder is like this. Okay. It is a normal distribution. Of course, it is not standard normal anymore, right? So, and what we want to arrive at is standard normal. Now, if you see intuitively that what choices of alpha can lead you to standard normal, right? So you may come up with your own choices, right? Because once you see this, you will say, okay, you asked me to go to standard normal, so my alpha t goes to 0. That's it. Right, so as t tends to to capital T, you assume that as t tends to capital T, alpha t tends to 0, and if this happens, then what you will be arriving at is x capital T, and this will be 0 because alpha t is going to be 0, and this will be identity. So this is nothing but standard normal, right? So a natural question is, are you free to just choose any sequence that goes to 0 or close to 0, because we are working with numerical thing. So so is it that you will choose any arbitrary alpha and just make it 0? So what is the plan for alpha, right? So we call this scheduling. Okay, so we will look into this. What exactly, what are the ways, good ways we can go through this, provided we also maintain a lot of things, right? So there are a lot of things going on here, right? Because there is prior matching here, okay? And so prior matching means like, I think there is some mistake here in this. No, this is fine. So this probability distribution produced this, yeah. So basically from here to here, I will come from xt minus 1 to xt, right? So probability of xt given xt minus 1, and this must match some p tilde xt, which is the standard normal, right? So this is prior matching, right? And then there are consistency issues, right? So the forward process and backward process, are they consistent with each other? Okay, we will see explicitly what it means. So basically the kernel divergence of the forward and the backward kind of should be minimized. Okay, so that we call consistency and so on. So there are these ingredients that will show up when we now go ahead and complete the elbow bound. So we left it at hierarchical VAE, and we had those Z terms there. Now with our plan of irrational diffusion model, we say that Zi's are Xi, okay, same sizes. We drop parameterization for the Q, which was so we drop parameterization for the Q. That's another plan. So we don't want any parameterization for. Okay, so with this we will have the variational, I mean the elbow bound for VLB. Okay, so we are kind of set up for going for a second round of the elbow bound, and I will write down some derivations because it gets a bit lengthy in the slide somehow, and I got some index issues at last moment. So few things are in the slide, but a few derivations I have to do it here. But let us see. This slide at least is okay. So as usual, we have this log likelihood, and in VLB we have this joint. So now we don't see Z because the notation is same. So it goes from end to end x0 to xt. Okay, so we have this simplified notation now, and what we want to marginalize is with respect to 1 to t, right? Obviously, because x0 was our initial sample, so x0 stands for sample, and the remaining ones are not necessarily samples. So x1 to xt, they are kind of like latent only, right? So they need to be marginalized out. So that's why we are integrating out from 1 to t, and the remaining x0. So you can think of these as x0 also. It's a generic. We have written p of x as a generic. It stands for x0. So we will marginalize out 1 to t. So as usual, these steps are very similar. Again, it is repetitive now. So we multiply and divide by q. So now we don't have q5, which is just q, because we don't have parameterizations for the forward process right now. So we multiply and divide by q, and as usual we take the expectation, right? So we take expectation with q, and then we apply the Jensen's inequality again on this. Okay, so until here it's same. Now we substitute the joint distribution, right? So the joint distribution in this case will be. So sometimes I may miss the notations theta. Okay, so in some places. So this p is parameterized. Okay, so you see them as parameterized. If I miss, it's fine. Okay, so. So we write the joint distribution for p, which is here on the numerator, obviously. So this is fine. For forward case, it was a joint from x1 to, in this case, actually x0 to xt. And no, this is like the reverse case, right? So this is t to 1. So the numerator is from t to 1, because this is the generator, right? So it starts from t and goes to 0. And since it starts from t, we can pull that out separately, because that's the root 1. So pxt kind of comes out, right? So the view we have is like this: x1, x2, dot dot dot, xt, right? So the joint distribution for this, right? So this is pxt, and then remaining one from 1 to, okay, is this correct? Yeah, that's fine. The last one we took out. Inside you will see there is a t minus 1, right? So it's okay, because if you write a t here, what you get here is t minus 1. So basically it is running until there. Okay. So so this guy is, just to like double check, right? So notations. So if we expand, right? So for t equals to 1, it's 0, x1. T equals to 2, and let us say for t equals to t is this x t minus 1 given xt. So this is all right. Okay. The last guy was kind of here. We pulled it out. So it starts from xt, right? So p xt, and then xt minus 1 given xt, and so on, x2 given x3, x1 given x2, and finally x0 given x1. Okay. So this expansion is fine, right? Okay. So, and for the denominator is a forward process. So so let's look at the denominator. But after expanding, kind of we get a intuition. So t equals to 1. So it's like x1 given x0, x2 given x1, dot dot dot, q of x capital T given x capital T minus 1. So that's fine. Okay. First term, the 0 we don't need, because it's a sample, right? So there is nothing to do there. So it starts from 1 to capital T. Okay. So denominator is also fine. Okay. So we are here. We are kind of here. Then we have pulled out some terms here. If you see this, then pxt was already there. Now we have pulled out p theta x0 given x1. So basically for t equals to 1, so this guy corresponds to t equals to 1. That term has been pulled out from the product, and the remaining one is from t equals to 2 to t. So that remains the same. So we have just pulled out the first term of the product in the numerator. Now if you look at the denominator, we have this time we have pulled out the last term from the denominator, right? So this is the last term. When small t is equal to capital T, then we have q xt minus 1. So that we pulled out, and our now product goes from 1 to t minus 1, because we pulled out the last one, right? Okay. Then we have combined the products. Now we to combine the product, how can we combine the product when we have, if we look here, when we have the indices are not the same. The numerator indices are going from 2 to t, and the denominator indices are going from 1 to t minus 1. Well, you do the algebra trick. If you can increase the t by t plus 1, then you are allowed to decrease the index. Okay. So this is the trick we did. So increase t to t, and all this will not change anything, right? So increase the t by t plus 1 and decrease the t in the index here by 1. Okay. And once we do that, so let us do that, because that step is not shown there. So t equals to 1 to t minus 1, p theta xt given xt plus 1. Okay, so if you look at this guy, we have done this here. Okay, decrease the indices of the product and increase the t inside, and all this will give me the same product. Okay, so nothing changes, but I did this because I saw that in the denominator, the indices were from 1 to t minus 1, and I wanted to combine, so I did this trick. So after combining, obviously you get this, and everything else remains the same. So both numerator and denominator are now with these indices of t equals to 1 to t minus 1. Okay, they are kind of combined. Okay, so I guess from here onward, I will try to write down the proof, complete proof from here onwards. So I am at this joint product, and then okay. So then we can split this product. Okay, because there is a log here. So if there is a log here, then log a times p is log a plus log b. So this is what we are going to do. Okay, and I will use the notes, otherwise I might make mistakes. So so after splitting, this will be e q 1 to t x naught. I will put these things in the slide. I noticed some index mistakes, so that's why I dropped those slides. But I will upload the slides correct one. Okay, so what we plan to do is that we split, right? As I said, I will split this. So basically it will be expectation of log of this plus expectation of log of this. This is what I'm going to do. Okay, so this is log of p xt p theta x0 x1 divided by xt given xt minus 1, and yeah, sorry, why should I do equal here? There's no equal here, this is expectation. Okay, so this is the first expectation after splitting, and then e q x1 to t x naught, and this is log of product of t equals 1 to t minus 1 p theta xt given xt plus 1 divided by q xt given xt minus 1. Okay, so I have just split. Okay, expectation of the first log term plus expectation of the second log term, and nothing else. Okay, so this step was also okay. Now we will do further simplifications. We will take out the p theta x0 given x1 separately. Okay, so we will keep that with the log, and then the remaining term xt, this guy and this guy, we will keep it separately with the log. So basically we are going to do one more splitting of the first term. Okay, so let us do that. So this is first term, and then now we write the second term. All right, this is only for this term. Okay, so this is only, we have expanded only this much now. Okay, and the last term remains as it is. Yes, nothing to change for the last term. So basically the last term, you just keep it here. Okay, this guy. or we can already write. So there is log of product, right? So we can change the log of product to sum. So that's a simple thing to do already. So let us look at the last term now. So the last term will become okay. Do you agree with this? Basically the product change into sum and log went inside. So that's trivial, right? So log of the product is sum of the log. So that's fine. We have like 2 more lines to do, and then we will be done with this lower bound. Yeah, so since expectation, we can use the linearity of expectation, right? So expectation can go inside the sum, right? So sum can go out, sum can come out, and expectation will go inside. So that will be the only change for. So let us, and there is no change for the first 2 term. So so let us do only this change for this guy. I mean, these are simple, but yeah, just for. And so basically expectation went inside. So let me put the sum outside. So expectation of the log, right? Log of p theta xt given xt plus 1 divided by q xt given xt minus 1. Okay, do you agree with this? So we just took the expectation inside and log sum outside, because expectation is linear, right? Expectation of a plus b is expectation of a plus expectation of b, right? So that's kind of trivial as well. All right, so then yes, some simplifications are needed. So basically, if we look into these terms, right? If we look into each of these terms, right? So if we look into each of these terms, let us say this term first. In this term, we have expectation of expectation with respect to x1 to t, right? Given x0. But what is there in the argument is only 0 and 1. Okay. So only 0 and 1 are inside are involved here. So we can certainly simplify this guy, and we can say x1 to t reduces to just x1, because x0 is already given. So this reduces to q x1 given x0. So this is the first simplification we will do. Similarly, you can think about this guy, that what are the variables involved here, and change this accordingly, right? So in this case, variables involved are capital X, capital T, and t minus 1. So then this also reduces to xt and t minus 1. Okay, and similarly we will look into this guy as well. The terms involved are t minus 1 and t plus 1. So only these guys are responsible. So we should change the notation to just t xt minus 1 and t plus 1. Okay, so these are also kind of simple changes to do, but for formality let us do this. So let me do that here. Okay, so this changes to so let us use oh, I was using red. Okay, that's not a good idea. Usually is blue. Okay, so let us see, let us now fill that, right? So then the first term becomes e q x1 given x0 log of p theta x0 given x1. So this was the first term anyway. So this was our first term, right? first term. Let us do it like second line. Okay, so the second term is EQ xt minus 1 xt. These are the only terms involved given x naught, and this is log p xt divided by q xt given xt minus 1. So this was our second term. Now finally the last term. In the last term, as we recall, last term is dependent on t, t plus 1 and t minus 1. So we are going to change the expectation notation with that. So the last term is outside there was a sum. So t equal 1 to t minus 1, expectation of q xt minus 1 xt plus 1. I could have written better, but it doesn't recognize my hand, so I have to write like this. So that's why it's not very smooth. Okay, and then the log p theta xt given xt plus 1 divided by q xt given xt minus 1. All right, so this is our third term. Okay, so let us verify. Okay, first term, expectation of q x1 given x naught, and the inner term remains as it is. So you can see this is the first term, and this is your third term. Okay, so first term, x0 x1, so we did that here, x0 x1, but x0 was already given, so we throw away x0, so only x1 given x naught. So that we did, x1 given x naught, and log p theta x0 given x1, so that remains the same. Now we look at the second term. Second term we had t and t minus 1. So we did that, we had t and t minus 1 and given x naught, and this term is the same. Okay, this term is the same. And then we look at the third term. Third term we have t minus 1 t t plus 1. So we have t minus 1 t t plus 1. Okay, so some notation changes we did. Right. Now we will change this into KL form, right? First one is log likelihood anyway, so that's that we don't have to do anything there. But if you see the second term and the third term, they are in kind of KL form. Okay, so we will try to write them in terms of KL. To do in terms of KL, if you see, the problem is in KL, the expectation that you take here, that guy is also in the numerator. So basically we need to flip this this log. Okay, we kind of flip these guys, because in KL the expectation term is on the top, right? And same thing. Now here it's a bit tricky. But at least we have to flip, because the Q is there, right? So both we have to flip. Let us flip and put a minus in front. Okay, so let us see that. First term we don't have to do anything. Second term, if you look into t minus 1 and t, then from Markovian we know that they are kind of dependent. So why should I take a joint with both, right? So if t minus 1 is there, then if t is there, then t minus 1 is determined anyway, right? So this is another a change that we are going to do. We will drop t. Okay. Yeah. So that will be for the second term. Okay. So let us go with the same way because we have less space, right? So let us do it term by term, right? And this is our third term. Okay. The first term we will not touch. Okay. Let us keep it that way. Second term we are going to modify, and the proposal is that Q is a backward or yeah, it's a forward process, right? So should you take joint with both t minus 1 and t? Because one is determined by the other. Okay. So the proposal is that we drop the t, because if I have t minus 1, anyway I can get the t. So these are some interesting tricks assumed. So let us focus on the second term. Okay. So the second term, and we will flip and we will put the KL, right? So these are the three things we have to do: drop t, flip, bring the negative sign, and write it as KL. So let us see the second term. So the second term we have. I will just copy over. Oh. Yeah. Q xt minus 1 xt given x naught, and this was log of pxt divided by qxt given xt minus 1. Okay, this was our second term, and what we are saying is that xt is kind of redundant. In a forward process, xt minus 1 determines xt anyway, so throw away the xt. So this, and then another thing is that we will flip the arguments of the log, and so that we have we can take the KL divergence. Okay, so just to cross check everything. Yeah, that's right. So so this is equal to I will take the negative already. I will do the flipping here. Drop the xt, and since we took the negative, then we are allowed to flip. Okay. Something is missing here. Okay. Did we draw? Because I see one more term there. Okay. They are not independent either, right? So Okay, so xt minus 1 xt given x naught, can we write this as q xt minus 1 x naught and q xt given x naught is this, and this is also expectation. This is only possible if it is IID. Yeah, it seems like this has been assumed here. Rather than dropping, but then splitting like this in general. Yeah, this has been assumed here, so I will kind of try to give a justification for that. Maybe I think last time when I taught, I had an argument for this, but so we assume this here, and if we do that, then yeah, so then it will change a little bit. So let us do that. So this becomes q xt minus 1 given x naught, and then expectation of q xt given x naught. Okay, this is how it is split, and then this is taken to be KL. Okay, so let us use this. Yeah, so this will be KL. So you see this in the denominator there is a q, and there is this q here, and so we can write this as KL of there's one more thing, it seems. Okay, so what is one more thing here is, let's see. So the way it is xt given xt minus 1. In fact, it's like this. So let us look at the graphical model for this. Maybe we will get a hint from there, right? So x0 guy is somewhere here, and we somehow went to xt minus 1, and we are looking at xt, right? And this is kind of given, right? So x0 is given, and we are looking at a joint of t minus 1 and t. So what we're saying is that the joint of t minus 1 and t is t minus 1 given x naught, and then you t minus 1 given x naught, and then xt minus 1 given xt. Okay, so that's how it's broken here. So the expectation that you will take for the joint xt minus 1 and xt, it could be written, because it's a chain, right? So it could be written as you take expectation from x naught to xt minus 1, and then xt minus 1 to xt. Okay, so yeah, so then we can, so this is our second term. Okay, we kind of leave it there, or like there one more step is there. We will write this in the usual KL divergence form. So this is expectation of q xt minus 1 given x naught, and this is our KL. So KL, and this is between numerator and denominator, right? So this is q xt given xt minus 1 and pxt. Okay, so this is the final form of the second term. Okay, any doubt here? So you may kind of see this if you want to prove this, why expectation would break like that, right? In a chain, in a Markov chain. Okay, so these are the results we are using it here. So this is our second term. First term is settled, second term is settled. Third term is also tricky, it seems, because it has similar form, right? It's a joint with t minus 1, t and t plus 1. So let's see what happens for the third term. Okay, third term. First, let us write down the third term, and then we will see. Yeah, so this is EQ. It is recommended that you watch my previous video, okay? I did this in detail previously, so maybe there are more. I did it on chalkboard. Okay, let's see this term now. This was our third term. EQ xt minus 1 xt plus 1 given x naught log of p theta xt plus 1 q xt given t minus 1. Right, so here the middle term is dropped in the KL. So let us see how the breakup happens here. So let us figure out the what we need for the expectation first, and then the residual expectation we will keep it kind of outside. Here as well, since the expectation is with respect to q and q is in the denominator, the first step is to flip. The expectation will be with respect to this distribution. So what will be the residual will be t minus 1 and t plus 1. So expectation t minus 1, t plus 1 will be the outermost expectation. Innermost one is t minus 1. That gets absorbed in the KL. Okay, so these are the steps we are thinking. Okay, let us do this. T equal to 1 to t minus 1. And let us first look into the KL part. So let us make KL happy first. So we have the flipping, so let us put that negative sign outside. Okay, so this is negative, so let us not forget this. This is a negative here outside. And okay, so let us first flip. Okay, so this is q xt given xt minus 1 and divided by p theta xt given xt plus 1. And what I need for KL is the numerator. So that expectation also I will pull out from this expectation that I have. So this is expectation with respect to q of xt given xt minus 1. Okay. So that I have taken out because I want to KL absorb this log term in the KL. Now what is left out? T I have taken out, right, from the joint. So what is remaining is t minus 1 and t plus 1. Even these things simplify a bit. You will see this later. Like I was using the initial argument, right? So if I have t minus 1, then t is determined. Yeah, these will be kind of used as well. But for the moment, t has been taken out. So let us keep the remaining expectation here. And we can do this splitting because of the Markovian assumption and so on. So we can do this as an offline assignment. Why expectation breaks like that, right? So t minus 1 okay, so I hope you can read this. So let us see. So we did the flipping of these log argument that brought the negatives outside, and this is the after the flipping, and then we pulled out expectation part which refers to the numerator because that's how I will develop KL there, and then the remaining expectation is kept outside. Okay, so overall now this guy is a KL, right? So we will just write that final step, and we are done with this VLB bound. Okay, this is the final step. So this is we will see what are the issues with t minus 1 and t plus 1, right? This is not feasible actually. T minus 1 is from the past, t plus 1 is from the future, right? So we have to do something for this term, but we will see. If, for the moment, let us keep it xt minus 1, xt plus 1, x naught, right? And the inner one is KL, so we just write this as, so the dKL of numerator and denominator, right? And then p theta xt given xt plus 1. Okay, agree with this? This is our final form. Of course, things are not completely clear, right? But that's the point, right? So we still have one full maths class we have to do to finalize all this. But so far what we have derived is the so-called VLB bound. It has 3 terms, and we have derived those. Okay, so this guy is called consistency term. It is consistency term because you can see there is a p theta. The distribution at time t, it's kind of trying to match the forward with the backward. Okay, so it's trying to match at each time step, or it's kind of, you can think of, it's trying to see the denoising that will happen will be matching with the noising one. Okay, so intuitively you can think like that. So it's kind of matching noising and denoising at each time step. Okay, so that's why it's called consistency, because this is the denoising, or from noise it's trying to go towards x0, which is the real image, right? So kind of at time t it is trying to learn the process of denoising that was done by the forward process via q. So we call this consistency term. If you can match this at each time step, then essentially you have learned to denoise and go back to the original image, right? So and then there is a last term which is a prior matching term. So that also is enforced by KL. So what this term is saying is that the final Gaussian that you are going to get, which is our favorite standard normal, this should match the forward distribution that you have, that you are coming from t minus 1 to t, you are about to get to t. So the distribution that will give you the final t, which is this guy, should match the distribution prior, which is standard normal in our case. So this is called prior matching term. Okay, so we have understood prior matching term, and we have understood the consistency term. Okay. And first term is there. So basically first term is like final step, right? So it's as if like there are 3 things going on, right? Boundary cases and the middle one. So the middle one is consistency. The last at time capital T is prior matching, and the initial one is reconstruction, obviously. So reconstruction means x0, which is our sample, given x1. Okay, so final step in the reconstruction. Okay, so we can see this as a reconstruction term. Okay, so this is our VLB bound. This is called, and this is a bound because there is a less than equal, right? In all our derivations, if you see, we had a less than equal at this step. After that, it was equality, but overall, it is less than. It is a lower bound. So sum of these 3 terms is a lower bound. Okay, and this is tractable. Like if you see right now, it is still very, very messy, right? How do I know these KL of QT, P theta XT? Okay, how do I compute expectation with even this guy, right? Past and future samples are involved. Prior matching, okay, which is again determined by Q itself. So basically it's about scheduling, right? You don't want to use neural network in the forward process, but what is your scheduling idea that it will in a clean way arrive at and match with the prior, which is standard normal. And then the first term is the usual term, reconstruction term. Having arrived at x1 during generation, what is your a good way, right, to reconstruction do this last part, right? So we have this VLB bound, and all these terms will be explicitly found out. Okay, and these will be the thing that we have to fill, basically all these gap. Okay. Yeah, I think from here onward, I think it was okay for the slide. Okay, so this is what we have. We have this log likelihood. We did the marginalization, integrated out the x1 to xt, and after doing all those calculations, right, we introduced the q, multiply and divide by q. We took the expectation with the q. Then we use Jansson's inequality to get a lower bound. Then we did a lot of splitting. We took the p theta guy out, and the prior matching term, last term xt out, and then there were some middle terms which are in the sum. Actually, this middle guy will play, obviously, because there are so many terms there, right? So most of the focus will be here. Actually, you will see these will turn out to be simple. So this is what I have written. This serves as a reconstruction term, estimates the log likelihood of the initial data sample premised on the first latent space. So your first latent is kind of x1. So this term is also present in VAE, where x1 is z. Okay, so the training will be analogous, and this middle one is a prior matching term, and then this is the consistency term that harmonizes the distribution xt by correlating forward and backward process. This is the forward process. This is the backward process. Okay, so so our focus will be on the consistency term. As I told you, this is the main computation bottleneck here. So our goal will be to know explicitly what is this explicitly, right? And because overall this whole thing will become a loss, right? We need to see the loss in full form so that we can build the algorithm and maximize and so on. So we need to learn and know about each of these terms explicitly so that it will go into the algorithm, right? So then our focus will be on the consistency term, this one first. Now in the consistency term, this is the troublesome guy, t minus 1, t plus 1. We have to do something about that. This also, what exactly is this? Q xt given xt minus 1, what is the expression of that, right? And what is this full expression of these? So these are the things we will see. Okay, so I will stop with this slide. Okay, with this remark. So basically we will be involved in this intermediate step where we have this consistency term involved with t minus 1, t and t plus 1. Okay, so it is good to focus just on this. So here obviously p theta does the reconstruction from it constructs t minus 1 from t, and then and this is the posterior. So this is written in a flipped way. Okay, so we call this like posterior. Okay, and this will come via chain rule basically. So basically we will get this via chain rule, which is actually this. Okay, so what we have is xt minus 1. Yeah, so what we have is this forward process, xt given xt minus 1 and x naught, but via base rule we can kind of flip this. Now it goes from t minus 1 to t. Okay, which is matching with this as well. Okay, so this will help us in sorting this out. Okay, because if we go in a parallel direction as this guy, as the p guy, okay, then this will help simplify a little bit. So we will see this in the next class. I will detail this step. So these are the things we want to do. The issue we have is to compute expectation with this t minus 1 and t plus 1. Okay, for which we will use base rule, and this issue will go away, you will see. Okay, okay, so I think let us stop here, because the next step that follow is again a big derivation. So anyway I have to start again next time. So with Bayes' rule, we will sort this problem, and this scale divergence expression will be explicitly derived in the next class. And other terms are also simple. So we will have the first complete diffusion model algorithm by the next class. And there are some modifications like score based and all this. So that can happen all these can happen in one class. Okay then, so let us stop.